Well, we have made it to the last podcast of the year. It's the last podcast of our energy unit, Calorimetry. We're actually going to be filling in pages 19 and 21. We're going to use the basic calculations on page 19 for both of the ideas on 20 and 21, but we just had to prioritize things with the amount of time we had left, so we're not going to be doing these combined calculations on page 20. But if you stay tuned and watch the podcast that I post next week, I am going to go over it, and it's just a straight kind of extension of what we're doing here on page 19. It should be pretty straightforward if you do want to get that filled in, but we're going to focus on getting to this calorimetry stuff on page 21. So, let's get started. The first equation that we see on page 19 is for phase change calculations. So, if you remember what we talked about with heating curves, phase changes involve changes in latent heat or potential energy. This is that stored energy that we don't see or kind of feel as heat, and like that we see as temperature change. So this heat is a really simple heat to calculate. In this equation, Q here is our heat or energy, M is mass, and that's going to be measured in grams. Then H is what's called the heat of fusion or the heat of vaporization. And we'll talk about both of them, but really this is just the amount of energy required to make a substance go through a phase change. So in the case of heat of fusion, this is the amount of energy required to make a substance melt. And you can see this as part of our equation over here. This 334 joules per gram is how much energy is required to make solid water, H2O, turn into a liquid. But you'll notice that this is also negative over here, because that's the amount of energy that is released when our liquid water turns back into a solid. So it's kind of the extra energy that's left over that isn't needed when it's a solid. So it's the same number, the only difference is the sign. And you'll notice the same is true for our heat of vaporization. The only difference is that this is when our water, or any other substance, is transitioning between a gas and a liquid. And this 2260 number for water is the amount of energy that we'd have to add in to get that liquid to turn into a gas, or that's the amount of energy that's released when that gas turns into a liquid. So we just have to pay attention to those signs. Positive for when the energy is being absorbed and going in from that solid to liquid to a gas, or a negative when that energy is being released, when we're going from a gas to a liquid or liquid to a solid. Now, in practice, these are pretty easy to calculate, because when it asks us to find the heat, that's going to be our Q that we're looking for. Here's my mass. It's just in milligrams, so I'm going to have to divide by 1,000 to turn that into grams. And then it does mention our temperature here, but notice how it's not changing at all. The temperature isn't important for these phase changes. All that matters is what the substance I have is and how much of that it is. So I have my mass, and then it says that I'm condensing this steam. So that means that I'm going from a gas to a liquid. That means I should be looking back up at the HV value that's given to me. And actually I noticed that they don't really match, so I'm just going to use the 2264 number. And this Q that we're looking for is equal to our mass times our HV. 2264, multiply that together, we get 11320. And this energy, this heat, is measured in joules. So that's my answer. Now, technically, we can use these HVs, heats of vaporization and heats of fusion, as conversion factors. That 2264 joules per gram is telling us that there's 2264 joules that's required to make 1 gram of a substance change phase. So if I were to start with that 5,000 milligrams, and even if I did take that extra step to say there's 1,000 milligrams in a gram, if I started off doing that dimensional analysis and maybe I just wanted to finish up the same way, then I could continue with this idea, putting that 1 gram on the bottom, 2264 joules on top, and when I multiply, I would get that same answer out. So, kind of two different ways of looking at this. And you might not think that that's much easier in this situation since we have the equation to calculate for heat. But if I'm calculating for mass, then maybe it's easier than doing the algebra that's needed to rearrange it, especially if I'm looking for mass and this HV that they give me is in joules per mole instead of joules per gram. I'm not quite sure what I would do off the top of my head, but dimensional analysis would help me. All I have to do, instead of guessing at my algebra and my rearranging and whatever else is going on, is start from my given. 500 kilojoules. Now, I do need to get that into joules, but I know that there's 1,000 joules in a kilojoule, so that's easy with dimensional analysis. And then from this point, this is telling me that there's 21 joules per mole. So 21 joules equals 1 mole. So I'm going to put the 21 on bottom because I have joules on bottom and on top. Make sure that decimal sticks. Put 1 mole on top. So if I wanted to know how many moles I'd get, then this is where I'd stop. But if I want grams, I need to go one step farther, and I'd need to add up the molar mass of this substance from the periodic table, which luckily I have. That adds up to 120.913 grams per mole. So it's that many grams equal to 1 mole. So I'm going to bring that 1 mole part down, put that 120.913 grams on top, and now I'm going to get a mass out that tells me how much of this stuff I'd need to absorb a certain amount of energy. And this might seem like a random question, but people have to do this type of calculation all the time for where heat sinks and making sure that cars cool, or that food that's going to be packaged and shipped stays cool. They need to absorb a certain amount of energy, and so they don't want to waste materials. How big of a cool pack do they need in order to keep it this cool for a certain amount of time? It's all very doable. Now, this happens to end up being a pretty big number. Long enough that I had to pause it to write it out and to double check that I wrote it correctly. And technically, I just want to keep these 3 sig figs here. So, 288, and then fill in these 4 zeros. It might be easier if I had this in kilograms instead, but it didn't ask for it, so we don't really need it. It's just easier to write and round sometimes when the numbers aren't so crazy. But either of these are correct. Whew. So, we're done with these calculations, and honestly, we're not going to do a whole lot more of them, but they are kind of an important basics before we get started with the next calculation. This question, though, no calculations involved. It just tells us that I have these 3 different substances, and each of them have these 3 different H's, and it asks which of these substances would melt first if they receive the same amount of energy. They're on the same heat source, and then which one would take the longest. So if we have to think about this H value is how much energy is required to cause it to change. So the bigger this number is, the more energy I need before it changes. So the thing that would melt first is going to be the thing that has the lowest energy barrier. I mean, the lowest number. So Z is going to melt first, and then it asks which one would take the longest. The longest is going to have the biggest energy barrier, and so this one is going to take the longest. Why? That's just because they have the highest H and lowest H. Not too bad. Now, sometimes we aren't just changing phase. Sometimes the temperature does change and the phase is staying the same. And in that situation, we're going to have to use a different equation. But it's the same basic idea. The Q that we're calculating is going to be based off of mass, but instead of an H value, we have a C value. And I'll talk about that in just a moment. Because the temperature is changing, the more we want the temperature to change, the more heat's going to be required. So we include that into our equation as well. So it's kind of the same idea, just with that temperature change there at the end. Now, this C value is very similar to those H's. This is the energy needed to raise the temperature. Instead of making it change state from solid to liquid, this is the energy needed to change the temperature of 1 gram of this substance by 1 degree. So it's the same idea, and in the same way that the H has an inverse relationship with these changes. When I have a very low C, a very low specific heat, means there's a low barrier to causing that temperature change. That means that it is going to have a larger change in temperature if you give it the same amount of heat as something that has a higher specific heat. That higher specific heat is going to have a smaller change in temperature if it is given the same amount of energy as that other substance. Now, what I had kind of glossed over, this is an intensive property, so it's something that you can use to identify a substance, because it's never going to change. No matter how much stuff you've got, the specific heat is the same. So this is a common property that's used to identify unknown materials found at crime scenes, etc., is take a very, very, very small piece and melt it, and we can identify it using that data. The C for water is there for you, 4.184. It has kind of crazy looking units there, and we'll talk about where those come from in just a moment. But if you do have other C's, and we will need them later, you might want to look at page 21. But this is the only number we're going to need for here, so we'll make a note of it and move on for now. The first question actually asks us to analyze this equation a little bit. We've already talked about it, so hopefully this won't be too hard. Q is our heat, our energy, and that is going to still be measured in joules. M is mass. We're still measuring that in grams. C is that specific heat thing we just talked about. It has those crazy J, G, C units. Think of C as crazy units, that's fine. But these units are actually designed to cancel out all the rest of these units. If we plug all of this in, then those joules and dividing by grams and dividing by degrees C just help cancel out all the other units that are here. So that delta T is our change in temperature, not just the first temperature or the second temperature. You're going to see two temperatures in these problems, and you have to subtract them to find how much that temperature is changing. And this is all going to be in Celsius, no conversions necessary though. So let's look at a problem. This first problem asks us to calculate the heat, so I am looking for Q. Required to warm up 750 grams, so that's our mass, of water from 10 degrees to 80 degrees Celsius. So the amount that my temperature is changing is by 70 degrees Celsius. So that is most of the information I need. I do need to go and find a C, and the C that we're going to be using is that C for water, 4.184. So just plug in all of this in. Now all we have to do is multiply all of these numbers, and what we get is 219,660. But we want to round this to 3 sig figs. So this is going to end up being, well, now that this rounds down there, it looks like it's 2 sig figs. So once again, it's a little easier to do this if this is kilojoules instead. We'd get to divide this by 1,000 to turn these joules into kilojoules, and then that would just be 220 kilojoules. So just a little bit easier to round that way and to keep those 3 sig figs there. But that's all that there really is to this problem, is find the numbers, multiply them together. In our next calculation, it asks us to find the specific heat. So we are going to have to rearrange that equation, but let's go ahead and find all our variables. Here I found my heat, my joules. I have a mass here, and it says that I'm going from 42 to 35. So here I'm technically going to be lowering the temperature of this substance by 7 degrees Celsius. So that's going to be my delta T. That's negative. And that makes sense because it also says that my heat is being released. So when I plug this in, this Q is also going to be a negative 20.4. So I could go ahead and plug all of this information into Q equals MC delta T and combine like terms and divide by anything that I don't know. I like to rearrange equations when they're kind of small enough for this, so instead I'm going to rearrange this. What I'm trying to find is that specific heat, that's C. So if I'm trying to find C and get C by itself, I'm going to be dividing each of these sides by M and by delta T. So that's what I'm going to be doing here. So now taking my numbers, 20.4, then dividing by 10, and dividing by -7. Now, if the negatives are confusing to you, honestly, it's not going to make that big of a difference to you right now to just drop them. But your physics teachers next year are not going to like that at all. So it's worth the effort to put in to wrapping your brain around what these numbers mean and incorporating them into your calculations, because they do have meaning. It's not just something we tack on there for no reason. So if I plug all of this in and calculate my answer, I get 0.291428, and I really just want to keep those first two sig figs, not the first three, because of that temperature there. So 0.29 and those crazy units for my C, of course. Now, technically this is my specific heat. And why is this useful? Because we can identify substances with this. So if you do go and look up the specific heat table for things, this is actually the specific heat for sand. So I'm willing to bet that there's a little speck of sand, as is this unknown substance. Now, this next problem I want you to do. You're going to be calculating mass, and it is going to be in the realm of 200 and something. So if you're on that kind of degree of magnitude, then you're on the right track. I would recommend you rearrange that equation. And the one thing I want to point out about this that's a little bit tricky is our kilojoules that were given for our heat and our energy. Go ahead, move that decimal 3 times or multiply by 1,000. That's going to be 9750 joules that you're going to be using there. I think everything else here is very doable. You should get an answer in the 200 range. What we need to do is jump over to page 21 and talk about calorimetry. And before we actually get started with our notes, I think that you know most of what's going to be happening here already. So if you think about it, what would happen if you put a hot metal into cold water? Like a hot spoon in cold water, or a flaming asteroid into the ocean. What's going to be happening with those temperatures? Here's some choices. Are both of these objects, the metal and the water, going to get warmer? Are they both going to get colder? Is the water going to get warmer while the metal gets colder? Or the metal gets warmer, while the water gets colder? Which do you think? Hopefully, you're thinking it's C, that the water gets warmer and the metal gets colder. And that's because there's going to be an exchange of energy. That hot metal, no matter what it is, has more energy than the cold water. And so it's going to be giving some of its energy to that cold water. And that's going to bring the cold water's temperature up and bring the hot metal's temperature down until they reach the point where their temperatures are the same, where they're not going to be changing anymore. That final temperature is not necessarily going to be in the middle of their other two temperatures. If you think about it, a hot spoon or a hot rock getting thrown into the ocean is not going to change the ocean's temperature almost at all, probably at all. But a flaming hot meteor will, because it's much bigger. It has greater energy, and more energy is going to result in a bigger change in temperature. So, even though those temperatures aren't necessarily going to change by the same amount, the total amount of energy transferred is going to be the same. So we're going to be talking about this idea. It's the big idea for calorimetry. The amount of heat energy that's being lost is going to be equal to the heat energy that's being gained. So, exploring this a little bit more, we've been using Q to represent heat instead of H or anything, so let's go ahead and update that formula a little bit. And then really, the situations we're going to be talking about really are mostly going to be focused on metal and water coming in contact. We use water because it acts predictably and it's easy to get, and so a lot of scientists have what's called a bomb calorimeter, which is just a fancy setup where they can explode things, burn things inside this kind of container of water, and all they have to do is measure the changes that the water undergo in order to understand better what's happening with that reaction. So this is kind of our general rule. The heat that the metal is going to be releasing is going to be absorbed by that water. And we're going to be measuring the temperature change of that water and using that to analyze our metal. So we're going to be using that Q equals mc delta T equation that we just heard about and putting it on both sides of this equation, which is going to make it a little bit bigger, but it's really just the same equation twice set equal to each other. So we have that mc delta T for the metal. It's going to be equal to mc delta T for the water. And this is what we're going to be using for these heat transfer problems, is this kind of big, crazy looking thing here. But what that means for us is it's really easy to solve these problems if we just focus on finding these three variables for each of our substances, and whatever we can't find is what we're looking for. So this is how I start each of my problems. You do have this big old crazy specific heat table here that we're going to have to use a little bit now and a little bit on page 22 when you're practicing on your own. But it's just here for reference. I don't have space to put it on my next couple slides, so make sure you're looking at that when you're trying to find your C. Now, first problem. Lots of words, lots of numbers. I have my little table set up over here because all I need to do is find these numbers and solve for whatever I can't find. So, tells me I have a 55 gram sample of metal. So I'm going to go ahead and write that down here. It says I'm at 90 degrees Celsius with my metal, so that's going to help me find my temperature change, but that's not the actual change yet. And it says it's dropped into a container with 250 grams of water. So even though it's not what I was looking for quite yet, let's write that down. That water was at 22 degrees Celsius. And then it says the final temperature is 23.4 degrees Celsius. What is the metal? So, let's see, 23.4 is going to be my final temperature. So technically I should be doing that minus these initial temperatures that it gave me, which means for my metal, it's going to be negative, which makes sense. It's going to be going down in temperature by 66.6 degrees Celsius. Okay. And then our water is going to be going up, in temperature by 1.4 degrees Celsius. Like we said before, it's not always going to be the same, and in general, water is not going to change as much because it has a very big specific heat. Now, it doesn't tell us about that specific heat, but while we're thinking about it, we always know what that is. And on this table that it has at the top, it says it's 4.18. I know it dropped that 4. Might freak you out. Just use that number as it's given to you for now. I don't judge you either way. So what we're looking for, I know it doesn't say specifically, but what we're going to be looking for is the C for our metal. It asks what is the metal, but this specific heat is going to be used to identify the metal. So once we find this C number, we're going to look back up in that table and see whatever it's closest to. So, in order to solve these problems, when we set all of this stuff up, we're going to plug in all of these numbers on either side of the equation. Okay, now, once we have all of these numbers plugged in together, I think the easiest way to solve these problems is to kind of simplify each of these sides here. So I'm going to multiply these two numbers together and just have that answer here by this CM and then multiply all of this together just to get a simplified version of this same equation. Okay, and now if what we're trying to find and solve for is this CM, I need to get it on its own, which means that I'm going to be dividing by 3663. And once I do this division, 1463 divided by 3663, then that tells me that the C for my metal is 0.399. That actually repeats, but that's the perfect number of sig figs that I need. Add my units, and then look back up at that table. And what happens to have a C of 0.399? Nothing exactly, but I do see that copper is 0.39, so that is the closest option that we have. So copper is going to be the metal that I assume that this is. And hopefully, if I was a CSI, I'd have a few more sig figs here, a little better measurements. But just identified a substance. Now, this next one is for you to do. So it's the same process. Go through and find those numbers, pull them out, do the multiplication and division, and you should get that your answer is aluminum. Now, I don't expect you to get 0.90. It's not going to turn out to be quite that nice. But the answer you get is going to round to be aluminum-ish. So do the calculation, find this answer, and with its precise answer, and you should agree that aluminum is our answer. And you have just finished your final podcast. Last little bit of work for you to do, other than the lab, of course, and have a little video intro to the lab if you need help with it. But it's a little bit of practice on page 22. 6 problems. And number 6 is the only one that's one of these heat transfer problems with all of these big crazy numbers. The rest are either Q equals MCAT or Q equals MH. And the way to tell the difference is to see if the temperature is changing. If you see a change in temperature, that means you got to use the delta T equation. And you will need some of the H's and C's and stuff from the tables on page 20 and 21. I know we didn't actually do anything on page 20, but if you're looking for an H or a C and you can't find it, it's probably there. Or, just get in touch with me and I'll give you all those magic numbers. So, there we go. That's it. We're done.